A warm welcome to all to a new session of ASAP online classes. Today we will learn about worm gear, which comes under Design of Machine Elements and Module 4, Semester 8 of Mechanical Engineering. The session will be handled by Dr. Jobin Varghese, Associate Professor, Adi Shankara Institute of Engineering and Technology, Kaladi, Ernakulam. We welcome you, sir. Okay, sir. Now this is an instruction for the students. The entire session will be of 1 hour, out of which the first 20 minutes will be the presentation, which will be followed by 10 minutes of Q&A session, that is question and answer session. Then again that presentation continues for 20 minutes and it will be followed by 10 minutes of question and answer session. For those who want to ask a question, should use the QA option available among the options which you can see under your screen. I'll repeat, to ask a question, you have to use the QA option available under the options which you can see in your screen for asking a question. Hope this is clear. So now we are beginning our session. Over to you, sir.
Okay, thank you. Thank you for the introduction. So this time we'll be working on worm gears, and last two sessions were basically on bevel gears as well as helical gears, and come to the worm gear, which is the last part of the module 4. And these are the contents which I would like to just convey today, that are the worm gear theory, worm gear design procedure, and worm gear demonstration problems. And if possible, some softwares which can assist you in just calculating that one as well. So the first part is as we have already covered some of the things like spur gears and straight bevel gears. It's in this session, and helical gears. As we can compare, there is a normal ratio, that is a ratio reduction velocity reduction ratios here. Okay, well, so we're just focusing on the efficiency, since which gear is better to be used. So in fact, you can see spur gears which comes up to 98%. Then it comes to straight bevel to 97%, and that comes to helical gear 94 to 98%. However, when it comes to the worm gears, it comes only to 50 to 90%. Although the efficiency is much less here, it is this acceptable in wide area because of its own usage, its own different uses. Okay, let's come to the worm gears. The major factors that can be designed on the basic parameters used for designing are Z1, Z2, Q, and M, where Z1 is the number of starts on the worm, and Z2 the number of teeth on the worm wheel, and diameter quotient, it's a quotient here, and a module, as we have seen, and we'll come in detail in later sessions. So it comes to the worm gear, we can see that, use a pointer here. Okay, come to the worm gear. This is a type of worm gear where exactly there is a 90-degree, the transmission of power and torque happens here, also 90-degree, but not necessarily. And again, we'll see this just shows the figures of the worm gear. And we come to here, and the major idea behind this one, or using a worm gear, is that one non-intersecting shaft. Like you can see, the axes are not intersecting anywhere here. So we are using to transmit the power in the non-intersecting axis. That is at right angles, but not necessary, preferably always in right angles. And the major benefit of this one is you can transmit high torque without failures, because many teeth are in contact at a time. Then when the high velocity ratio reduction is required, when the high velocity reduction is required, we'll be using this worm gears. Then other disadvantages and advantages, when you see that, the major advantage is that can reduce the velocity as high as 300:1, which is in a very perfect designing and manufacturing when happens. And it's in a single state with a minimum space. This is a major advantage. It's like in a single state itself, it can be reduced. That what I mean by velocity reduction is that if the motor is running at an RPM of 3000, again, that can be reduced to 10 or 15 within a single step. It doesn't require multiple like the spur gears or helical gears, where we are just combining many gears to reduce the velocity ratio. However, in the case, what happens is that you can, in a single step, as well as the space, which is quite compact, this does not require, unlike the gear train which we are using the spur gears. But however, there's disadvantages like has very low efficiency. And the other one is that it cannot be interchangeable. That means we can use a different worm for this one if the diameter is increased. For example, the thread pitch, the distance thread pitch. In fact, what do you mean by distance between the gaps are same in a bigger diameter also, we cannot use this type of pinion. We call it a pinion here for the different things. So we cannot interchange between this one. The same pair has to be used. However, in the case of helical as well as bevel as well as spur gears, that's not a problem. Then it comes that's another major disadvantage here. Then comes here like the pinion gear. We just consider this as the pinion. That's because there is a less number of teeth on this one, and we consider this as the gear because there is two parts for the pinion, like worm wheels, like worm as well as the gear or worm wheel. We call it as, and worm is considered as the pinion, or worm is this one, and worm wheel is in fact this one is the gear with number of teeth. And you can see in many machines, you can see this gears, and mostly in industry, will be seeing this type of gears. Yeah. And this shows a small animation of this one, how it's work. You can see that there is an inclination over here, which actually pulls this gears upward. When you rotate, the inclination of this gears, you can see the teeth have an inclination over the pinion, which push or just moves this gears, whatever worm gear. Next comes the operational characteristics of worm gear set. So that's I already discussed. Like in fact, it will not be working. Suppose we are changing this one to a different wheel. Like this is a pinion, we are taking this one to a different wheel, having a bigger diameter. In this case, what happens is that one, it won't work here because it won't mesh clearly. That's the reason why we cannot interchange. That is the operational characters when it comes. Then comes specifically to the worm. When we see there is some basic parameters to be understood, and this is the shaft which will be connecting to the worm pinion of a part or the worm. So this is called the pitch diameter, that is the pitch circle, the distance between the pitch circle. Then it comes the worm pitch, that is pitch is from starting from the point to ending in the same point, which is called as the pitch, and it's along the worm axis. The only condition is that it should be measured along the worm axis. Then comes the helix angle. So helix angle is like when we draw like helix, and extend the helix to this one and making just an angle with the pitch circle, or maybe axis. You can consider as the axis. So it is the helix angle. Then comes the lead. This lead is like when we turn one time, how long it will move, how much it will move. This will be moving in like a screw. We can assume like a nut and bolt, or maybe a screw. So when we rotate one time, how much linearly it moves, that is represented by the lead. So don't confuse between the pitch and lead. In fact, this is the linear distance it will move. This is the measurement over the pitch. So you can see there are different types of worm gears here. So we call it as lead or single start. Right? I'll just show you in detail in the next slide. So there are different type of slides here. So in this case, there is called a single start, double start. So single start means only one thread which will go around this one. And the double start, you can see a single turn starts here, another turn starts here. Two turns will be in a helix angle, it will be winding over this one. So major advantage is like you can see the gap between these two. This will hang this much gap, this hang this much gap. Means there is a precise movement possible in the double start. However, precise movement is not possible in the single start. Also, more load can be taken in the double start. And when we just go into the reality, when you can see that this is one thread starting, this is the other thread starting, which together are winding together. So when more precision required, more number of starts is required. And in fact, you can see this a number of having different starts, like one thread, two thread, three thread, four thread. So four threads will be starting front and will be going so quite precise, and the pitch angle will be less in case. And when you come to this point here, the lead angle, when calculating the lead angle for a single start thread, you can see lead angle is the distance between two pitches. However, when you come to these cases, it is not that one, it will be between two, because two threads in between there is a one thread. So totally is equal to 2 times the pitch. In the case of it will be 3 times the pitch. There will be a difference in the lead. That is the movement which is going 3. We have to calculate 3 threads we have to pass to get the lead. And some other parameters to be introduced is the angles here. So you can see first one, I just come to the lead angle. This is called the lead angle, which is represented by gamma here. So when we draw a tangent here, and when we take a surface that is perpendicular to the axis of this one. So this is the perpendicular surface, and this is the like a tangent to the helix angle. So this is the helix circles to the tangent. When we have an angle that is called a lead angle, the angle of the lead. So we can see that one, that is the vertical. When we take a vertical of this angle, with the vertical we get this lead angle. And in fact, this is the helix angle. So here, how we are not using this one, we are using helix angle as beta. So here beta, when you see the axis with this one, the helix, again the helix which the axis of, in this one you can see horizontal. Vertical when comes the lead angle, horizontal comes the helix angle, and there is another called the pressure angle. So pressure angle is the angle between the pitch. So there is two leads here, two threads here. Between that one, what is it? And half of that will take us alpha, which is the pressure angle. We consider when we draw a vertical over here, we'll get half of this one. So alpha is the pressure angle. So these are the three angles which we'll be using in this one for the calculations. And worm gear, different types of gears are here. So in fact, first I come to straight face worm gear. In the straight face worm gear, it's like usually we use a helical gear. Our Varghese creates more sounds when compared to the helical gear. So in the case, what happens is that the teeth will be in the straight axis. That is also the axis of the worm will also be in the straight. That is the gear, worm gear as well as worm will be in the straight. The axis will be straight. So what happens if the contact area is much lesser and a single point is actually transferring on each teeth, like what will be the contact, each single point will be transferring the force. However, in the case of second one is a half straight face worm gear. In this case, you can see there is a curvature here. The curvature is found over the teeth. Like on the teeth, you can see a curvature. So this curvature, when measures with the like worm, what happens? More contact area comes into being. That again we will see in our section. So and finally, we can see that concave face worm gear. So here there will be a concave on the teeth. Also, the teeth is having a small concave, like a cone structure. So totally the contact area will be more in this case, and more force can be or torque can be transferred. And this is well explained here one more time in a detailed explanation. So in fact, you can say this is a straight. So we just again classify this one worm gear set into three, like non-throated, throated, and throated having single envelope and double envelope. So which I have already explained. This is another classification where we can see this is a non-throated, means there is no throat over the teeth. So it's all, everything is straight. Now it comes to the throated, in which single envelope is like, as I've seen that you can see there is a curvature here over the teeth. There's a small curvature on the top of the top line of the teeth. And third curvature, when in the side view, you can see there is a small curve which is formed with the system. That is, in this case, that curve cannot be seen. However, in this case, more curve. That is, it is in more contact with the worm. And in the third case, that is double. In the case of double enveloping, the reason is that it is called as double enveloping because this is also bended. The axis here is also bended. Also, this also bended. In both cases, it's bended so that the contact area is much higher in this case when compared to this one, where more amount of force can be transferred. And in normally worm gear arrangement, worm is the driver and the wheel is the driver. Usually we take in such a manner. And worm wheel, we come to the worm wheel. Maria explained about the worm wheels. So in fact, this is the worm wheel and it is having a helix angle. When we this is the teeth. When we draw along the teeth like this way, and we take the angle that the helix or the edge. And there are two types, like right hand worm wheel and left hand worm wheel. As you have seen in the helical gear, again against rotation, we are just keeping our fingers and seeing that how this the thumb is pointing. As per we'll be taking, if the right hand thumb is pointing towards this one, we take the right hand worm gear, and in this case the left hand worm gear, which I will just already discuss in the helical gears mostly. And this is the first part of this one, and we are coming to the design part here. Okay, so before I start to design, is there any specific questions?
Sir, as of now, we don't have any questions. So we can continue the session for now, and we'll ask the questions at later.
Yeah, sure. Okay.
Okay, sir. Okay.
Yeah, this session requires much more time to explain, so that I've just gone through the theory in a faster way. So in the case of design of worm gears, there are steps like almost 8 to 9 steps we have to complete when compared to helical and bevel gears. The first section is like, obviously we have to select the material for any design. So in fact, we have given the reference to 0.7, page 234. In that one we can take for this one. And usually we use the material as worm is hardened steel and the worm wheel is phosphorus bronze. This is the usual material we will be choosing. Suppose the material is not given, further we can take it from this page title 12.7, page 234, we can see that the material there. Next one is we will be finding the weaker part. Always we are designing the gear based on the weaker part. Here, although we are not following the same procedure as we are just we are following the bevel gears as well as the helical gear. Here we will be taking the worm wheel as the weaker one. The reason is that when the worm wheel always slide over the worm, the structure is such a way that, and the helical angle is such a way that. So as a result of rubbing, there will be overheating happens, and which leads to failure. So when heat happens, there will be changes in the strength of the material, and as well as the failure may happen. So obviously, the additional factor which has to compare with the we have to calculate in the case of worm wheel is the heat, which dissipated and generated. And the third comes, so in the third or second steps comes, we have to find the diameter. So first, we are classifying the problems based on center distance is known and otherwise center distance is unknown. In the other cases, we were classifying with the case of diameters, which diameter is known, which diameter is unknown. In this case, center distance means the distance between two gears, that is worm as well as the worm wheel. The distance is known. So once the distance is given by the letter A. So we can calculate directly. If not given, we have to use this equation, that is power, which will be given how much power we have to transmit. Then from this I dash is the transmission ratio, that is N1 by N2. From this we have to calculate what is A. Once the A is calculated, again further we have to go for other calculations. Then comes to the module, where the module equation is Ft equal to sigma d CVP ym, where we can see in 12.53, page 223. And the parameters here we can see is sigma d, which mostly will be given. If not, we have to take them from the data book. Then we can see the CV, that is velocity factor, then B phase width, and Y is the form factor, and N is the module. From this one, M can be calculated. What is M? So here Y is changed to pi M. That's the difference here. All these factors can be used, and in the problem, in a problematic discussion, I will show you how it can be done. And then comes to the finding the lead angle, where I have explained what is lead angle. So you can see that when we take a plane that is normal to the axis of this worm, as well as when we take a tangent from the worm, there will be angle called, we use this angle gamma as the lead angle. We have to find out the lead angle, tan gamma is equal to mz by d1. Then we have to, as we have already done in other gear designs, we have to use the dynamic tooth load. We have to find out what is the force that is occurring during running. When the gears are rotating together, there will be additional force will be acting because of different factors coming into being. So even if a friction is there, obviously friction should be there, and dynamic forces are coming into the scenario. And as a result, and the thrust forces, many forces are coming into this one. A dynamic tooth load comes here. So that should be calculated. Then second one is you have to calculate the wear tooth load. The wear tooth load, in fact, what is meant by wear tooth load is the maximal load at which the wear can take place. So obviously, if the dynamic load is equal to wear load, that means it's not in a safe condition. How we can run it for some time? The major condition is the wear load should be greater than dynamic load. Fs is represented by dynamic load. So as a result, if the wear load is greater than dynamic load, then even though some force is extra added to that without, apart from designing because of the external behavior, the gear will not wear. So that is the major thing here. Then comes to find the efficiency, and we have to calculate the efficiency based on this equation. So the major is that worm drives the worm gear. Here worm gear drives the worm. So in two cases in the data book is given and two equations, we have to use that. And all the parameters required from theta can be calculated from this one. And that's the rubbing velocity, then our friction. So all these things can be calculated here. And then the final comes to the heat generator. In fact, the heat generator means like as there is a rubbing happen between the worm as well as the worm. As a result of rubbing, in fact, the heat is generated, and this heat should be dissipated, or else what happens, the metal is getting highly heated, and finally the failure occurs because of this reason. So this is the equation we can use in this one, and Fn is equal to Ft by cos alpha, cos gamma, cos alpha. This from derivation I haven't seen in the data book till the Mahadevan. I hope it has to be understood and learned this equation for just calculating heat generator. Then heat dissipator is given by this equation. So dissipator effect is maybe by a natural convection, or maybe if the forced convection is there, obviously that the heat will be dissipating. However, what we are doing is like we are comparing heat dissipator and heat generator. If heat dissipator is greater than heat generator, obviously artificial cooling is not necessary because heat is rejecting out is greater than generator. So it's in a cool condition. In the other case, the artificial cooling is necessary and the fan should also be provided. So this comes to the demonstrative problem. So we come to demonstrative problem. This problem design a One Gear drive. So it has to transmit 2 kilowatt of power at 1000 RPM. The speed ratio is given as 20 and center distance is 200 millimeter. Assume number of teeth on the worm wheel is 40 and number of starts on the worm to be 2. Assume hardened steel and phosphorus bonds. Obviously, the material is already given. Sigma D. That is, this is the permissible static stress that is given. Then check the gear for the standpoint of strength and wear. If load stress factor K is equal to 0.69 megapascal and if the amount of heat generated is 1.7 kilowatt, check whether artificial cooling is necessary or not for a temperature rise of 40 degrees. So there is a temperature rise is given. In fact, we have to check whether artificial cooling is needed or not. So that is the major thing. So I just listed out all the given parameters here. And what design for strength and wear, that is the thing. And here this factor is like temperature T2 minus, that is rising temperature is 40 degrees. So when running 40 degrees is generating heat is generating us is 40 degrees centigrade. That's just temperature. So temperature and heat is quite different. Okay, we'll come to that. And it comes to this first part, like we have to find the material selection. So as I've seen that page number 234, there is a material has to be selected for this one. However, in the case already the material is given, so we don't want to select, or else we have to just take this one and we can find out the sigma D from the material if not given. Here the sigma D already given. And the second part is to identify the weaker gear. Obviously, I told the worm gear is the weaker part because of the generation and rubbing happens over that one. Parameters I carry over this to this one. The third step is second step is like finding diameters. We have to find the diameters of the both the gears. So in fact, you can see in the case of this one, for speed reducers with integral worms, the AGMA recommends a mean pitch worm diameter. So this is the worm diameter which is taken as the D1. So using the equations, A is the center distance which is already given. From this one I have taken A and we calculate D1 equal to 75 mm. In the case, we have to calculate D2 where the center distance is given using the equation. We know what is A, we know what is D, and D2 can be calculated. Now the first parameter like diameters of the both worm and worm wheel has been calculated. Next, we have to calculate the module. In fact, this is like a little bit lengthy. However, we have to take care of this one when calculating. So we can see that one in the third step. The permissible tooth load according to Lewis equation is because the module will be calculating based on the Lewis equation, that is the static case. So because we have to mesh together, initially the meshing happens in the static case, then only the dynamic force come into being where Buckingham theorem will be further following. So Ft equal to, there is an equation. From this we can see a module here. So sigma D is already given here. Sigma D already we have a 55 megapascal, and then we have a CV. CV value should be find out, and so CV can be find out from this equation, that is 6.1 by 6.1 plus V, where we should find out from here. So you can see V is equal to, in this equation V is equal to, because we are designing for the gear, worm gear, we are using D2 N2. We are not going D1 N1 because driver is pinion and driven is worm wheel. So from this velocity is calculated and substitute in this one. In this figure we'll get CV. So we already find CV, sigma D, and unknown is B and Y. Then we have to further go for B and Y. Remember that N2 is required in calculating V, where N2 can be calculated from the gear ratio. So this we have to use some more common sense how to calculate all the things by relating. It may not be always same questions, but we should know that I equal to N1 by N2 is equal to Z2 by Z1. So all these things should be, we should have now D1 by D2 by D1 should be in our mind. Then Then comes the second part is like as I told, like sigma D already calculated, CV already calculated. We have to calculate B and Y. Well, we are coming to calculate the Y. So okay, here we calculate the FT. FT is calculating with the equation FT equal to 2 MTE by D2, where MT is equal to MT into KL. There is a factor called KL. So we have to calculate what is KL. We come to page number 248. There is a KL, but it's not specified anything. So we are taking this one as a steady load campaign plow. It's a steady load. We are choosing this one to make our calculation easier. So we are taking the steady load. KL is taken as MT is calculated. And MT is, I can see MT is calculated, and 2 MT by D2 we will get what is FT. So once we get FT, this parameter is also found out. And next comes we have to calculate the Y to come. So whatever I have found out, always I'm updating here. So all the things which I already previously found, updating here. So we are calculating M2, CV, V2, everything is updated. Then we have to calculate what is the factor called Y. So in fact, we know capital Y equal to pi into NY. So before that, we have to calculate what is this Lewis form factor. For that one, first we have to take Z1 equal to, this is the number of threads. 2 threads is having. So we'll go into this one and see single and double threads. In the page number 244, single and double threads, we have to get the pressure angle. The pressure angle alpha. And when we get the alpha, we have taken from this table 12.28, that is alpha is equal to 14.5, we get that. And we are choosing 14.5 and Lewis factor Y is found from this. And this Y is like substituted here, pi into Y, and we will be substituting Y. So like we can get Y equal to pi into Y, there is 0.1, we'll get this one. So we have calculated the form factor. And finally, only thing is that base width. And obviously, you can see somewhere here. We can get it from a different table. However, the reason behind this is we don't know the pressure angle and exact Z1 equal to 2. We don't have a measurement that is given in the table. So as a result, only we have gone through this way. If given directly, obviously we can go through that as well. Then finally, we are calculating B, where B can be calculated B equal to A power by 2. Direct equation and calculate. Now substitute and find the module. We'll calculate the module. So I'm updating the next, that is what is module. Next comes to the module is 2.88 calculation, and it has to be standardized from the table 229, that's page number 229 table 12.2. We can see that module is 3, that is we are standardized. And I have dated as module, may be used in as for the calculations. Then next one, we have to calculate the lead angle. So lead angle having the equation, we can use in the equation 221. In this one, D1 equal to Z1 M2 by tan gamma. So all these are we are selecting depend upon the given equation, what the parameters given in the question. That's available. If not available, obviously we have to choose a different equations according to the data given. So here we are using that one, and from we have to calculate what is gamma. So gamma is equal to, we can calculate the tan inverse is Z1 M2 by D1. And gamma is here 4.57 degree. The next one is the dynamic tooth load, and dynamic tooth load is represented here as the Fs equal to sigma d bym. I think all the parameters are already given here in the sigma d. For this one is given, and it's for B. We have calculated B, and Y calculated M. Everything is calculated. So finally we can calculate the dynamic load. Now we have to calculate the wear load. So wear load equal to D2 BK. So in fact, K is a factor which is already given in the question. So as a result, we don't have to go for that one. K is already given, or else we have to find out from the table 12.30 if not given. As is given, we are taking directly here. Then D2 is already given. We know what is B, and we know K. So from this one, we can calculate. And finally, this is the conclusion here. So once we calculate 12.33, so we say FW, that a wear load is greater than dynamic load. Now, when we divide, you can see 12330 by 28516, almost 4.3. That is the factor of safety is 4.3. Even though some external force act on the gear and increase the dynamic load, what happens? It can increase up to 4.3 times what's the load acting right now. So it's a very safe condition. So we can move with the further designing. Next one, the efficiency. So efficiency, the equation is given our efficiency when the worm drives the worm wheel. That is equal to eta equal to cos theta minus mu tan gamma by cos theta plus mu cot gamma. So from this one, we have to calculate what is tan theta, where theta should be known as an unknown here. Tan theta is equal to tan alpha cos y from the page number 224. And we can calculate what is theta, substitute theta, and also gamma is already, we know what is gamma. And then the major thing here is what is mu, which is not given, where we have to find out what is mu. So for calculating the mu or the friction coefficient, you can see we can use the equation. The reason is that one, the greater speed than 2.75, this equation should be used. So as we have seen the velocity, when we see the velocity, you can see it's like we have calculated the velocity v equal to pi dn by 60. So in this case, okay, before that I'll just have a parameter y is selected. Okay, vr is equal to pi dn by 60. We have found out 3.94 second. Again, we are calculating the velocity here, v pi dn by 1000, where the velocity of the pinion. So it is 3.93, which is greater than 2.75. As a result, we are using this equation. If it is less than, we have to go for this equation. So v equal to, we are finding and finding the factor. Now mu equal to 0.0375. Now all the parameters we are calculated for the efficiency. Now substituting, and we are finding efficiency equal to 66.92. So remember that already I have just shown you, that is usually that comes One Gear have efficiency from 50 to 90. So this comes in between 66.92. Next part is finding heat generator. So heat generator, usually we will be finding the equation in the page number 227, this one. However, heat generator is already given in our parameters, so we don't have to calculate this heat generator. And so here there is a Fn. Fn is factor is Fn is a normal force to the tooth surface. So Fn is equal to Ft by cos gamma cos alpha. This is calculated from the derivation, and I haven't seen anywhere in the data book. Obviously, we have to just know about this one, or we have to derive from this equation. There is a diagrammatical equation where we have to calculate from this one post analysis. So heat generator is already given, and then we can go for heat dissipator. So heat dissipator, we have to find out the equation for heat dissipator, and then that should be solved. Now we can see that one heat dissipator, another equation for the heat to be is equal to Q equal to 0.407 by this equation. The reason why we are using this equation is there is a factor called T2 minus T1, where in the question is asked to find out for temperature, change in temperature, T2 minus T1 equal to 40 degrees. So that we are using the equation. Temperature is not given. This equation can be used where this is an approximate calculation without temperature. Now there are factors called Ag and AW. Ag you can see here, this in the page number. Ag equal to pi by 4 d square area of the worm gear, and where AW is equal to this projector area of the worm, that is LW into D1. Where we have to calculate what is LW, we can come to 243 page number, where that is LW is the phase length is given as 14.4 plus 0.063Z1 into M. So this we are taken for single and double threads. Our thread is a double thread. When it's a triple thread, we have to calculate this one. However, the equation is same for both. Now calculating all the values here, that is we are calculating Ag, AW, LW, and substituting, we get what is the heat dissipator equal to 1402.85. Now the conclusion comes is that one heat dissipator is 1402.85 is less than heat generator, that is 1700 kilowatts, which is already given 1.7 kilowatts. So sorry, 1700 watts. So this in between, as you say, QD is less than QG. As a result, what happens is that the dissipator is less than generator. So more heat is generating all the time. As a result, we have to give some artificial cooling. Artificial cooling should be given for this one. And that's the problem we'll be solving for this kind of things. And I have used the references here. And thank you for this section. And maybe if you have some questions, you can ask. And I have to show a software demo where you can just work out if you're interested.
Thank you, sir.
Yeah,
So we have some questions.
yeah, sure.
Sir, I'll read it out for you.
Yeah.
So the first one is, as wear and tear is high for this worm gear,
Yeah.
is there a special kind of lubrication needed? If yes, please explain.
Yes, obviously lubrication is usually we'll be using the lubrication, but however, as the point of in the real design we'll be using this one. This is as per the academic point of view, where the lubrication layer is not considered or sliding layer is not considered in this case. So whatever is like when the lubrication comes into the factors has to be taken, like the viscosity of the lubricant and the reduction in the friction coefficient. Everything has to be calculated, or we can take the friction coefficient and reduce it to the lubricating things. So that happens in not in academic point of view, which is very tedious and you cannot complete within that hours of examination. The calculation cannot be complete. That's why reason I think academics are not included in this.
Okay, sir. So another question is, for calculating module, why do you take CV 6.1 by 6.1 plus V?
So that is a general equation that is given in a data book, which is which I have not taken actually. So
Okay, sir. Okay.
that is I can show you if you want like identify what this. Okay, I hope you might have seen that one. I've taken the equation directly. It's not nothing. It's already proven. Okay, you can see here. This is taken already given in this one.
So that means it is a proven equation, right?
Yeah, it's a proven equation by the
Okay,
database provided.
Okay, so another question is, what is the difference between worm and a worm gear? Is there any difference?
Yes, you had understood what I just taught about. So you see, we say, I'll come to the picture first. Okay, as we see in normally in the sport gears we say, or in the helical gear we say, there is a driver as a driven. So always this one is the driver. That is this called the worm. The worm is the driver and this is the driven. We will be connecting this to different shafts, output shafts, and this will be the motor. The electric motor will be connecting to this shaft. So this first this will electric motor will be the rotation to this one. Again, that will be transferring to this one. So the major idea is to reduce the velocity ratio. The velocity is 8,000 RPM means if we require only 100 or 50 RPM, then we can use this. So that's the major reason behind it. If I have answered the question.
Okay, sir. Hello. Sir, another one is there any self-locking mechanism on worm gear and
Yes. Yes. Obviously, I haven't spoke about that one. There is a self-locking mechanism. Is like it can only go forward. It cannot go backward. That's why the reason the major application we are using that one in the cranes. That is in many elevators, all the things. It cannot return back. Only in one direction it can rotate. The other one is a self-locking mechanism. Obviously, there's a self-locking mechanism. Yeah, that's a point I think I have missed. So
okay, so that means the self-locking mechanism is for it is not to go backwards.
Yes. Or even you cannot rotate Pinion Gear as well. We cannot rotate the worm wheel. We can only rotate the worm only. We can rotate only the worm. We cannot rotate the worm wheel. If needed, we have to change the design.
Okay, so another question is there any mathematical relation between lead angle and helix angle?
Okay. So as of now, I have improved, but we have to take it from the theory, like the slide here. Okay, you can see this is the lead angle, this is the helix angle. This is related like this. If you just add together, what will be the relation? That is gamma plus psi, or usually beta is used in database. So gamma plus beta equal to 90 degree. So we can use that relation if needed.
Okay, sir. Okay.
No, audio is, I cannot hear.
Oh, so there are two equations for calculating efficiency of worm gear. will it be specified in the question, is the driver or the driven part?
Say like since I told like we are designing this one as that we are taking the worm wheel as the weaker part. Means worm wheel will be always a driven one and worm is the driving one. So that is the usually weak case for the academics. In fact, we are not going for the other case. So that for some reversing actions or to brake when required, we'll be using that type of designs. So in fact, you can go with this one only, that worm is the driver and the other worm wheel is the driver. So obviously there won't be any confusion in taking design part.
Okay, sir. So another one is, so what are the areas of applications where worm gears are used? And is there any areas where only worm gears can be used, even though the efficiency is very low?
Okay. So the first of all, you have to understand that the major thing is like the worm gears are majorly used for velocity reduction. So that's why I told you, like, when we take an electric motor, it can run all over 2000 RPM. For example, I can take a machinery case. For example, some case of a machinery where rollers are running. To have in Jindal Steels Industries, we can see the two rollers are running. The steel is in between that one so that it can flatten more. So the major reason the velocity should be well controlled, or else there will not be flattening of the steel happens. Also, the rollers will get damaged. However, in the case of an electric motor, it will run at 2000 RPM or like that way. As a result, what happens is that if 2000 RPM the rollers are running, what happens? The rollers will get damaged, steel will get damaged, the product will not get. So when we are applying a worm gear, the major advantages is that it reduces in a single step. A single turn itself, what happens is that 3000 RPM will be reduced to 50 RPM. And that depends upon the ratio, how we are just calculating, how we are designing it. Then second one is that the space is much less required. The machine will not be bulky. As like in the Varghese, we have to use the gear trains. There are many gears combination to reduce this. Also, major other application, we can see that one in the elevators because it will not rotate back. They have a braking mechanism. So all these things we can be used as.
Okay, sir. Another question is, what type of worm gears are used in indexing mechanisms in gear cutting?
Can you repeat the question? I didn't hear it clearly.
Okay, sir. So what type of worm gears are used in indexing mechanisms in gear cutting?
Okay. So what is the need of using a worm gear in indexing cutting? It's if the efficiency, when we compare with the efficiency and high load to be transferred, we'll be using the worm gears usually. And indexing cutting, in fact, I don't know exactly what type of worm gears are using there. But usually I haven't seen the worm gears, and when there is a speed reduction required and efficiency high, we can use such things. I hope that is that you have to find with the companies what type of they're using.
Okay, so I think the question is clear. So again, one more question is there. So is there any derivation for the normal force equation function?
Okay, normal force equation functions. Can you make more clear on that one?
So I'll ask him to make it clear. So another question is, one more question is, sir. So what about the metallurgy of worm gear, and what are the common materials which are used to make worm gear?
No, this as per the academics, as like as we can see that we see the bronze. You see, you can use a bronze and phosphor gear bronze. Steel can be used for this one. So this depend upon you can see all the materials here. Usually, what is your requirement? How much force we have to transfer? So we will be selecting sigma d based on the material. That is, we are always we will be just comparing the static with the force which are recalculated. If the static stress, if the calculator is greater than static stress, obviously that will fail. So what is your application and what is the power to be transmitted depend upon the material has to be selected based on the sigma d values. That doesn't mean we cannot, it's not restricted. However, there is restriction in the manufacturing methods. If it requires, like when we have to make the worm wheel, specific manufacturing methods are required. So in that cases, obviously, we have to limit the materials, as per easy manufacturing.
Okay, so the last question was, is there any derivations for the normal force equation function?
Okay, again, the same question happens. So,
this is a derivation function, sir. Normal force equation derivation function. Is that clear?
like if I want to refer that one, if there is such things, is there, and maybe I hope. Okay, let's go. So I hope I are is asking like something about this force, that is this normal force derivation function, like a normal force is there, and the derivation for this function or something. Or else you can contact, like there's an email ID.
Okay, sir. Okay, sir. We'll collect the question and we'll collect the question and mail it to you. You can answer later.
Yeah.
So we'll go to the last question. Sir, what are the applications of double, triple threaded, and four threaded worms?
Yeah, that's I told the major reason or the major idea behind creating such worms is that one, like when we require a precise movement, like the pitch movement is very precise, as well as when we have to just transfer high amount of power, that is more number of threads are coming into contact with this one. In that cases we'll be using. So generally that is costlier when you use. So when we make a gear, we have to take care of the cost with other applications. That is whether that worth in the business. If so, we can go for that. So that such applications are like precise and specific applications will be only going for such things. In normal case, as I have seen the robotics and everything, they are using a single one. Means that much whenever precision required, we go for that.
Okay, sir. Okay. So with that, we are coming to the end of the session,
Yeah,
sir.
just a second. I have to show. I have to show one more thing here.
Okay, sir. Wait.
Okay, so okay. So I hope the screen is visible. This is Autodesk Inventor. So if you are passionate enough, like we can see these things without just designing in these cases. Like we can go to assembly. That is we can go to file new assembly in the Autodesk Inventor. Once we come to the assembly, we can go to design in this part, and many components you can see over here. And apart from, I'm just showing you worm gear. So we can take the worm gear. So like sorry, I have taken the worm gear. Okay, this when we take the worm gear, you can see the design part here. So design part having many components. As I said, the center distance, you can change the center distance, or can choose the center distance. And there is a calculation part here. I'm not showing any how it's doing because it should be a different session to do that. So all the things you can work out on this one if you require. And remember that one exact whatever the calculation what we are doing done already may not be obtained from here, because this is considering a practical way of doing these things. We are calculating addendum clearance, root fills, and as you said, lubrications if required. All the things are calculating materials and Poisson's ratio, worm material coefficient. All things are calculating, and finally we are designing this gear, exact gear. So if you're interested, like we can go to Autodesk Inventor, which is an actually educational package which are always assisting education. and can design. Also, moreover, there is another called the ANSYS package here. So in fact, this can also be used to analyze this one, and you can you can use the static structural to learn very easily. This can be learned. So static structural part can be used for easy learning, and if you require for some movements and everything, then obviously we can go to the explicit dynamics session. And okay. Okay, you can see this dyna explicit dynamics is there. So you can take this one and learn like this way, but to have more idea on the design part. This can assist you in learning. So with that, I just completed my classes.
Okay, sir. It is really happy that you use all efforts to clear all doubts, and that was a wonderful session, sir. And it was well explained too. And we hope that the session was helpful to each one of our attendees. So thank you, sir, and to all who took their time to attend this session. Thank you so much.